So this is the solutions to suggested problem set number 2.1, mostly considering vector quantities for motion. So we start off with the rhinoceros at the origin of a coordinate system at time 0. So here's our rhinoceros. It's just a dot. For the time interval from 0 to 12 seconds, the rhino's average velocity has an x component of 3.8. So we'll go ahead and just highlight this. We have an x component of 3.8 meters per second and a y component of 4.9 meters per second. At time 12 seconds, what are the x coordinates and the y coordinates of the rhino? So I'm going to go ahead and start by just writing an expression for my velocity, or really my average velocity, in vector form. So my average velocity is just given to be negative 3.8 in the x direction, so I can write that as negative 3.8 I hat, and in the y direction, 4.9 j hat. So this is just me rewriting the stuff to begin with. So I want to know at time 12 seconds, what are the x and y coordinates of the rhino? So if this is my average velocity, I know that average velocity is defined as delta x over time interval. And so if I rearrange this really briefly, I can see that my change in position would be average velocity times my time interval, which I'm starting at 0, so I can just write that as t. So for each part of this, so this could be delta x or delta y really, my first part of this is just going to be finding the x coordinate using the average x velocity. So my delta x will be equal to v average in the x direction times t. So that will just be negative 3.8 multiplied by my time of 12 seconds. So my change in x position, since I start at the origin, is simply going to be negative 45.6 meters. Then my y direction, same deal, just with a different quantity. So I'm going to use my average velocity in the y direction multiplied by time, which is just going to be 4.9 times 12. So my change in y position will be positive 58.8 meters. So these are my x and my y coordinates. So I could write that as xy, or I could write it as a position vector, which I think I will do. So negative 45.6 I hat plus 58.8 j hat. So there's my x and y coordinates for the rhino after 12 seconds. Thankfully, I wrote this as a vector, so the next part is how far away is the rhino from the origin? So my vector is something akin to this. So I'm negative in the x direction and positive in the y, so I'm up here somewhere. And I want to find this position. So I get this from a triangle, right? So my x is 45.6, my y is 58.8, and this right here is my vector r, so that is my distance. So this distance, or the magnitude of this distance rather, is going to be square root of negative 45.6 squared plus the square of 58.8, which, if I throw this in my calculator, gives me a distance of 74.4 meters. So it's a very simple start off to dealing with two-dimensional motion. Question 3.4 begins to involve a little bit of calculus. So I'm going to go ahead and just start by seeing what is given. The position of a squirrel given by something in unit vector notation. So I'm going to go ahead and rewrite this just to make sure I'm absorbing it. So I have, for the I direction, or the x direction, 0.28 times t plus 0.036 times t squared. And this is in my x direction, or my I hat direction, plus 0.019 times the cube of t in the j hat, or the y direction. So question A asks for the vx of t and vy of t. So these are my velocity expressions in terms of time for the squirrel. So I know that the x component will come from taking the time derivative of the x position. So really I'm just looking for d dt of r with respect to x, my x position. I can do the same thing for my y off to the side, right? I'm just taking the derivative with respect to time for each component of this. And it's really convenient if I know how vectors work, because this left-hand side is my x direction, and this expression right here is my y. So vx of t is just going to be the time derivative of this part of the component. So that's going to be 0.28 plus 0.072 times t. And this is my x velocity expression. For the y direction, I am just taking the time derivative of this term, which works out to be 0.057 times t squared. And that's all there is to finding my components of velocity as functions of time. Now part B asks us to go to 5 seconds and figure out how far the squirrel is from its initial position. So how far implies that we're looking for a distance. So I'm going to take my my position function as a function of time, and I'm going to go and substitute 5 seconds for my time. So I want to find the position at 5 seconds. So this is going to be 0.28 times 5 plus 0.036 times 5 squared, and this is in the I hat direction. Then I have 0.019 times 5 cubed for the j hat direction. So my position at 5 seconds is going to be 2.3 I hat plus 2.375 j hat. And so that's my position at 5 seconds. But I want to know how far I am from my initial position. That means I also need to know where I was at time 0. Well, thankfully, every single term in my position function has a time component. So I know that my initial position is really 0 in both coordinates. So how far away am I? Well, this is my position vector, so I am somewhere up and to the right, and this position should just be given by some trigonometry. So go ahead and use Pythagorean theorem to find this position, or this distance rather. The magnitude of r will be the square root of 2.3 squared plus 2.375 squared, all square rooted, which gives me a magnitude of 3.31 meters from my original position. Now part C asks the magnitude and the direction of the squirrel's velocity at 5 seconds. So I want to find velocity at 5 seconds. So I have a component in the x direction for velocity as a function of time and the component in the y direction. So I can recall that my velocity vector works the same way as my position, where I have my x component times I hat and my y component times j hat. Or I can go ahead and rewrite this using the two velocity functions I've already found as 0.28 plus 0.072 t, and this is times I hat, plus 0.057 t squared j hat. And so this is my velocity as a function of time. So now I just want to find velocity at 5 seconds. So I'll substitute in 5 for all of my instances of t. So I'll have 0.072 times 5, and this is my I hat. Oh, I have one too many parentheses here. Plus 0.057, that is not a 7, 0.057 times the square of 5, j hat. So going through this entire process, substituting and using a calculator to find all of this, I end up with a velocity at 5 seconds, the vector being 0.64 I hat plus 1.425 j hat. So going through the same process I essentially did for position, I'm going to use Pythagorean theorem to find the magnitude of this velocity vector, which is just the square root of 0.64 squared plus the square root of 1.425. I'm sorry, the square of 1.425, all square rooted. So this magnitude works out to be 1.56 meters per second. And my angle comes from using the arctangent of, so we'll say theta equals arctangent of the vertical component over the horizontal component. So that would just be the arctangent of 1.425 over 0.64. Pardon my small handwriting. And so my angle works out to be 65.8 from the calculator. However, let's make sure that we're getting the correct answer because we do have tangent here. So if I sketch my velocity vector, I have a positive x component and a positive y component. So I should end up with something in approximately this direction. So yes, this does appear that I could have an angle of 65.8 degrees. So I will report that as my angle above the x-axis. Moving on to 3.5. So here we're going to be talking about acceleration. So we have a jet plane flying at a constant altitude with components of velocity given at time 0 and components given at time 30 seconds. So first off, the problem asks you to sketch the velocity vectors at t1 and t2. So I'm just going to make a nice big set of axes and sketch both of them. So we'll say that the positive y is up and the positive x is to the right. So I'll use two different colors here. We'll do red versus blue. So at time 0, I have an x component of 90. So we'll say 90 is about right here. And 110 is approximately about right here. So it's a little taller than it is to the right. And we'll say that this is my velocity vector at time 0. So we'll call this v1 because it is t1 rather. t1 is 0 seconds. So this is my velocity at 0 seconds. Now at 30 seconds, I have an x component that is negative 170, so way over here, and a y component that is positive 40, so it's slightly up. So my vector here will be way off to the left, and this is my velocity vector at time 2. So how do they differ? Well, one is up and to the right, and the other is up and to the left. One has a positive x component, one has a negative x component. Both have positive y components. So for this time interval, so I'm going from t1 equals 0 to t2 equals 30 seconds, I want to calculate the average acceleration. So how do we do this with a vector? Well, average acceleration is defined as the change in velocity over the time interval. So first off, what is my change in velocity? Well, let's go ahead and write our two velocities as vectors. So v1 as a vector is given to be 90 I hat plus 110 j hat. Velocity 2 given as a vector is negative 170 I hat plus 40 j hat. So my average acceleration, since it's defined as change in velocity, is going to be v2 minus v1 over my time interval, which is just 30 minus 0 seconds. So plugging this in, I will see that I have negative 170 I hat plus 40 j hat minus my initial velocity vector, which is 90 I hat plus 110 j hat, all over 30. So this is simply vector addition or subtraction at this point. So for my I direction, I have negative 170 minus 90, so that is negative 260 I hat. For the y direction, I have 40 minus 110 j hat, so that it works out to be negative 70 j hat all over 30 seconds. So plugging this in and doing a little calculation where I'm not left with fractions, I see that my average acceleration works out to be negative 8.666, which we'll round to 8.67 in the I hat direction, minus 2.33333, which we'll round to just 2.33 in the j direction, and this is going to be meters per second or meters per second squared. So this is my average acceleration vector. Now part C asks for the magnitude and direction of the average acceleration. Well, actually, I guess part B asks for the components. So this is the x component. This here is the y component. But we accomplish both of these just by working with vectors. So C, however, is asking for magnitude and direction, which is easy at this point. So the magnitude of my average velocity vector is just going to be the square root of negative 8.67 squared plus the square root, or the square of 2.33 squared, which works out to be 8.98, or about 9 meters per second squared as my magnitude. And the direction works just like we would for velocity. So real quick, if we sketch my acceleration vector, it should be to the left 8.67 and down 2.32. So this is approximately my average acceleration vector. So that means that my direction, which comes from the inverse tangent here, of the vertical component, which is going to be a y over ax, and if we substitute, that is negative 2.32, or 33 rather, over negative 8.67, this gives me an angle of 15 degrees out of my calculator. So I need to be careful here because this 15 degrees is right here. So I could really leave it as 15 degrees, but I need to make sure that it's 15 degrees below the x-axis in the negative direction. So I can say below the negative x-axis. And that is specific enough. You could use an alternative definition. You could say that it is 195 degrees from the positive x-axis, but be sure you're specific. Now I will point out, because it is important, that my acceleration vector is in actuality this difference in velocities. It is v2 minus v1. So I'm actually accelerating in this direction. So this change in velocity is really my acceleration vector. So, finally, for question 3.7, I am given the coordinates of a bird flying in the xy plane, and I have two position functions. So I have an x position function, which is given as alpha t, so I'll substitute alpha, which is 2.4, and I have a y position function, which is given as 3 minus beta t squared, so I'll substitute that as well. And part A asks you to sketch the path of the bird between t equals 0 and t equals 2 seconds. So, since I have basically a parametric system here of equations, I'm going to plot points on a set of axes. So first I'll sketch a set of axes, the vertical being positive y, the horizontal being positive x, and at time 0 I have a coordinates of, let's see, so time 0, x of 0 would be 0, y of 0 would just be 3. So we'll start and we'll say here is my first position. Then I'll just go ahead and say at x equals 1, my x coordinate is 2.4, and at y of 1, my y coordinate will be 1.8. So let's see. So if this is 3, then 2.4 is about right here, and 1.8 is about right there. So here's my second point. Then at the 2-second mark, my x coordinate will be 4.8, and my y coordinate will be negative 1.8. So let's see, that would be about the same distance in the x direction, but down here in the y direction. So if I'm sketching my path for the first 2 seconds, it's going to look something like this, something parabolic, right? Because we're accelerating in one direction but not the other. So B asks us to find the velocity and acceleration vectors of the bird as functions of time. So in order to do that, I'm going to rewrite my position functions as one position vector. So I can write this as 2.4 t I hat plus 3 minus 1.2 t squared j hat. So my velocity vector will just be the time derivative of my position vector, which will just be 2.4 I hat minus 2.4 t j hat. So this is my velocity vector as a function of time. And my acceleration vector will just be one more derivative beyond that. So I'll just take the derivative of my velocity vector with respect to time. So the x direction does not change. The y direction is simply just 2.4 j hat. So you'll notice I did not even write the I hat component because there is no I hat or j hat. There is no I hat direction for acceleration. Part C asks us to calculate the magnitude of direction of the bird's velocity and acceleration at 2 seconds. So I'm going to go ahead and do C off to the right here. V of 2, so if I plug in 2, will just be 2.4 I hat minus 4.8 j hat. So the magnitude of this, again using Pythagorean theorem, will be square root of 2.4 squared plus negative 4.8 squared, all square rooted. So the magnitude of the velocity at 2 seconds is going to be 5.37 meters per second. And then my angle comes from the arctangent of these two components with negative 4.8, the vertical component on top, over 2.4. So I get an angle of negative 63.4 degrees. So let's go ahead and make sure that this makes sense. So at 2 seconds, the slope of my position function is somewhere down and to the right. So yes, this could be my angle defined from the positive x-axis. So that is fine. So here's my magnitude, and here's my angle for velocity. For acceleration, however, it may be different. So my acceleration vector at 2 seconds will just be negative 2.4 j hat. So thankfully, the magnitude of this is really easy since it's one-dimensional. That is quite simply 2.4, and this is meters per second squared. So that's quite easy. I don't need to do any Pythagorean theorem because it's really just one-dimensional. And my angle, I'm not going to do any math here either, because if it's only in the j direction, that means it is going straight down. So my acceleration vector is somehow straight down at the 2 second mark, which means that the angle would be defined as negative 90 degrees. So you can see we have two different directions for our velocity and acceleration vectors. Now, D asks us to sketch those vectors at 2 seconds. So I already did this. I already got ahead and I did D. They're sketched right here on my drawing. And at this instant, I want to know if the bird's speed is increasing, decreasing, or not changing. So how do I know if the speed is increasing, decreasing, or not changing? Well, if acceleration and velocity have any components in the same direction, then speed should be increasing. The second part of part D asks us, is the bird turning? If so, in what direction? Because my velocity seems to be pointing to the right while my acceleration is straight down, that means that there's some component of acceleration that is perpendicular to my velocity, which is causing my bird to turn to its right. So if you want to see this in a better understanding, so here's my velocity vector, and there's some amount of acceleration that is going this way, and there is some amount of acceleration that is going this way. So the component of acceleration that is parallel to the velocity causes speed to increase. And then the component that is perpendicular causes turning. So here you have our solutions to this problem set.